Everyone. I'd like to welcome you to Hendrik Makait, Session Dask Xarray Geoscience at Massive Scale. Hendrik is a data and software engineer working on Dask at Coiled, and I'd love to hand it off to him. Thank you so much, Hendrik.
Thanks, Stephen. Thanks everybody for joining me to my talk on Dask and Xarray, which are a true power couple for running geoscience workloads at massive scale. So without actually any further ado, let's dive into this and do some geoscience. For this, first of all, we need some hardware to actually run stuff at scale. I've actually, before this talk, I've used Coiled, my employer, to spin up a Dask cluster of 100 VMs on AWS. So we have this up and running, and we can now go and crunch some data. So as a data set for today, I've picked the National Water Model. This is a data set published by NOAA in the US. It's essentially, some geospatial data set. And this allows us to, in this demo, compute the average depth to soil for every county in the US over time. Here, we're loading this data set into Xarray. We're actually interested in the depth to soil, which is hidden behind this very cutely named variable. And we see that this is 250 terabytes of data in total over the entire time that it's available here. Because I want to keep this demo short, I'm actually subsetting this to just 3 years, so 2018 to 2020. And this is still 18 terabytes of data, so still a large amount of stuff that we need to churn through. So with this data actually being loaded, what we now have to do is we actually also need to be able to take each of those individual points all over the US and be able to match them to some county in the US. For this, we're loading another data set. That's in this case just 1 gigabyte of data, so very tiny in comparison. And yeah, let's get to our actual computation. It's not too fancy, but it gets the gist done. So what we do here is we do a group by operation, we group by the individual counties, and then calculate a mean over time and the individual data points that we have per county. The result of this in the end will just be 210 megabytes. So we're really condensing things down here. So let's kick off the computation. This will not take a moment until the computation arrives on this Dask cluster that I've already spun up. But yeah, what you see here now is the default Dask dashboard that any open source Dask cluster that you spin up has available. We just now saw our computation arrive. And this gives us a very good overview of what happens on your cluster at the moment. So we see we have like 110,000 tasks that are being processed. We see the progress that we're making on the individual workers up here. We see the general progress we make toward our main goal down here. And then we also see like what the memory utilization is on the individual workers, if they're all saturated with tasks. And we can also dive deeper into individual components here. So we can take a look at individual workers, for example. Now, the main downside of this page is that this is just real time, so nothing is stored. It's not available after the fact. So if you're interested in that kind of stuff, that's where observability tools like Prometheus come in, or well, managed deployment services for Dask like Coiled. So what I've switched to here now is the actual page for the cluster that I've spun up. We see the computations that I've run. We also see even more metrics, and we see these metrics over time that shows the health of our cluster. So for example, we see the workers CPU utilization. That's looking okay. It's at 50% for the individual workers. Like, could be better, could be at 100, but if we scroll down a bit, we also see that we have quite a bit of network data transfer going on. So that's probably bottlenecking it here as well. If we're interested in this, or we see errors later on, we also have the logs available for these clusters, and all of that stuff is then stored over time. You can take a look at what your production process has been up to, even long after your cluster is shut down. So while I've been talking, this computation is starting to near its end. So it will finish in like 3, 2, 1, very long 1. My timing wasn't good this time. So now it's done. And over in a notebook, we see that we have the final results. So this is just the 200 megabytes in the form of a NumPy array. And if we visualize this, what we'll see in the end is this nice map of the US with the average depth to soil over those 3 years that we had. And yeah, here we've just processed 18 terabytes of data, and in total it costs us like $3 in cloud computing costs, which is quite nice. So let's talk a bit about the tools that we have available and that we've used to run this geospatial workload at massive scale. First tool I want to talk about is Dask. Dask is fundamentally a library for general purpose parallelism in Python. What that means is that whether you have some for loopy code like this, where you have a bunch of files that you just want to process in parallel, you can totally use Dask to parallelize that or just scale that out to a fleet of machines. But also if you have more complex stuff like pandas data frame computation that you'd like to scale out, Dask has a parallelized API of pandas that also mimics the semantics that pandas has baked in. So it makes it very easy for you to scale out your computations to an entire cluster. Similarly, for array workloads, it has a parallelized version of the NumPy API, which also allows us to scale out those computations, as we've just seen in the Xarray example. But since it's a library for general purpose parallelism in Python, Dask also allows you to take whatever complex and dynamic workload that you have and express it in Dask and then scale it out to machines. So the image on the upper right here, that's an actual Dask computation from a Dask user. You can see that this is more complex and more convoluted than what you'd usually want to express in, say, a MapReduce style paradigm that other systems implement. So much for Dask. The other library that we used here is Xarray. And Xarray in a nutshell is NumPy, but with labels. We all know this. NumPy is a great library, but it's a bit tedious because we have to remember that axis 0 is actually time, axis 1 is latitude, axis 2 is longitude, and none of that meaning is actually baked in. So people have gone and set out to add those labels. We've seen this in our example already. So if we scroll up quite a bit on where we loaded the data set, we saw that our dimensions suddenly have a meaning. So the first dimension is a time dimension. That's nice to know. But not only that, also the individual data points, the individual indices in that dimension have a meaning now. So the first index is actually this particular point in time. And what this allows us is to use this meaning and then do, for example, the filter operation down here in a way that makes a lot more sense for a human who's reading this data set compared to some indexing by numbers on the 0th axis. Xarray also allows you to group together several NumPy arrays or several NumPy matrices. So for example, in this case, it would show the temperature and precipitation share the same dimensions and the same indices. Now, where the magic really comes in is if you combine those two together. And what this looks like is what we've already seen in the demo. We express our computation in Xarray. And then when you want to compute this, Xarray actually creates a Dask computation graph. Dask then hands off this computational plan to a cluster that you've spun up, well, wherever you have your machines lying around. So whether that's Kubernetes or AWS. If you have a Slurm HPC cluster around, you could also spin up Dask on that. Or last but not least, as we've done, we can use a managed service like Coil to take care of the deployment of Dask for us. And now you can run this will run your entire Xarray computation on a fleet of machines in the cloud, close to the data that's also stored in the cloud. And this is a game changer because we don't have to transfer data from some US bucket onto my local machine. We have way more computational power than I could have on any desktop. Now, for the remainder of this presentation, I want to talk about Dask and geospatial applications. And the two things I want to focus on here are some of the improvements that we've made to the Dask Area API over the last year. And I also want to talk about the geospatial benchmark suite that we are building out at Coiled. And first of all, why it's important for us as Dask developers, but also why it's important to you, the Dask users. When talking about improvements in the distributed array computations in Dask, the first thing that comes to mind here is rechunking. Rechunking is a very notorious operation in any distributed geospatial workload because we've already seen the data sets are huge. Like the 18 terabytes that we've just processed, they wouldn't fit onto any available machine on AWS. So what we have to do instead is that we have to chunk up this data set, to slice it up into tiny pieces, hand off those tiny pieces to the individual workers, then let them perform some sub-computations on those pieces and combine those things together in the end to create our end result. Now, the most notorious case here is if you have a data set that's chunked in space and you need to shift it to a data set that's chunked in time. Like imagine you have a data set of satellite images. So you have like one satellite image per day. And that's also how it's stored on disk. Now, what you want to do is you actually want to calculate, say, the mean over time, over many years for each of the individual pixel on those satellite images. And now you suddenly have a big problem because each of the individual inputs that you have, each of the individual input chunks, contributes a tiny piece of information to each of the output chunks. And in the past, this has been huge trouble for Dask because the way Dask handled this was with task-based rechunking, which in essence created the Cartesian product between inputs and outputs, and then took these to create a huge amount of very tiny intermediate tasks, which would eventually overload the scheduler and just limit the ability of Dask to scale in general. Now, earlier this year, we've made the P2P rechunking system the default in Dask, at the very least for the cases where it makes sense, for those all-to-all rechunks. And what this system does is that it essentially circumvents the task-based paradigm that we have in Dask It just uses it for synchronization and concurrency control. All of the actual data transfer, all of the actual rechunking then happens in an out-of-band system that's purpose-built for this. How this helps us is that it first of all reduces the number of tasks from n log n in the legacy implementation to O of n, so it allows us to scale linearly. And it also, the P2P implementation has a much better means of controlling the memory footprint, so the memory footprint will actually remain constant. Now, I want to make this a bit more practical with a demo. So first I thought, let's actually test this for a data set of like a terabyte of data. That's not too much. It's something we can do very easily. When I tried out this demo, it turns out the legacy rechunking implementation was so bad that a scheduler with 64 gigabytes of data would eventually just run out of memory while trying to materialize the task graph. It wouldn't even kick off the computation. And this is a scheduler that's way bigger than what I'd usually choose. Like usually I choose one that has, say, 16, maybe 32 gigabytes of RAM available. But so you can still see the difference between those two methods. Let's have a look at this at the scale of 100 gigabytes. That is a scale that even the legacy implementation is able to handle. I've prepared a small video for this in the interest of time. So we're kicking off the two computations. On the left is task-based legacy rechunking. On the right is P2P rechunking. So this now takes a bit of time because we actually need to do some pre-computation. We need to send the task graph over to the machine. So this was from my German notebook to the US. Takes a couple of seconds. But yeah, here around 1 minute in, we see that P2P is already kicking off. We see that we have roughly 55,000 tasks that are running, and it seems to be going very smoothly. Like there's very little white space here. Task-based rechunking is now here as well. It's starting to kick off. We already see that we have 3 times the amount of tasks here. And remember that task-based scales non-linearly. So with 1 terabyte or even 10 terabytes, the difference would be vastly larger. We already see now that P2P is able to maintain a very constant memory footprint, but for task-based rechunking, this is building up constantly. So if we skip forward a bit, we'll eventually see that, yeah, task-based rechunking now starts to actually spill data to disk because workers are running into the memory limits that they want to occupy. And this also now slows down the entire computation. This still functions very smoothly and with a very constant memory footprint. So yeah, so much for that. I'm going to cut that short a bit. P2P will also finish faster. But yeah, let's get back to our presentation. The second improvement I want to talk about is downscaling. Downscaling as a workload is essentially smoothing our data set along the time axis. If we just take a look at the computation that we execute for this, it's rather simple. So we have, well, 2 rolling means really. It's not too complex. And in this example, we have a data set of 26 gigabytes, like less than 200 chunks. So this shouldn't be too bad, right? This shouldn't be too hard. Well, actually, if we just run this on this data set, we get this warning. And it tells us that for some reason, the amount of chunks in our data set has exploded by a factor of more than 30. That's pretty nasty. But, well, seems to be related to stuff being out of order. in that case, what we usually do if something's out of order, let's try sorting. That should solve our problem, I guess. No, this actually made it much worse. So suddenly we don't have a factor of 30, we have a factor of more than 300 more chunks. What this means in our example is that while we started off with less than 200 chunks, we now have 67,000 chunks. They're super tiny, so they're like below 500 kilobytes. So each of those individual chunks, when it's being executed, the overhead related to this will be taking up most of your wall time there. And because this has exploded so much, even a trivial operation like multiplying this data by 2 will now add at least like 67,000 tasks. So with that, we've gone back to the drawing board and re-implemented the whole algorithm. And the outcome of this is, as we can see here, that the new implementation keeps the number of chunks mostly stable. It's mild increased by almost 2, but it's same ballpark. I have a demo prepared for this, but I'll just skip this mostly in the interest of time. If we just take a very quick look at the video here, we see with the old implementation, we have more than 300,000 chunks. And the scheduler is very, very busy here. We don't see much happening. And when we do, we have these almost always white space in here. So that means that the overhead is dominating this entire thing. In contrast, with the new implementation, we have just 40,000 tasks, which is a big improvement. And while there's still a lot of white space here, it's able to complete much faster, as we can see in the progress down here. Now, what I still want to talk about is geospatial benchmarking. That's what I'll use a few more minutes before we jump into the questions. Why do we need actual geospatial benchmarks? Why is that interesting? For that, I want to talk about Dask data frame. Over the last year and also in the beginning of this year, we have essentially re-implemented the Dask data frame API. And while we were doing that, there was obviously, as always, more work to be done than time of developers that we had available. So we needed some function that allowed us to optimize what we're focusing on. And for this, we picked one of the available industry benchmarks for tabular data that are around there. So specifically the TPCH benchmarks. And by focusing on improving those benchmarks, which are also end-to-end benchmarks, we were able to, over time, get to an improvement of a factor of 20, which is significant. Now that we're working on Dask arrays, we actually want to do the same. The problem is just there is no accepted industry benchmark for this. So we need to make up our own. What that means for us is that we want to have a suite of benchmarks that are, first of all, end-to-end benchmarks. So they should focus on the entire workload that a user wants to run. Because we've seen that in end-to-end workflows, the bottlenecks might be surprising if you compare it to benchmarking individual atomic operations. Since I'm working for Cold, we focus on deploying large-scale workloads on large-scale clusters. That's why we also want to focus on large-scale benchmarks. So if your workload runs on like 10 gigabytes of data, we probably don't care. If it runs on a terabyte or 10 terabytes, then we definitely care about your workload. And the last point is that we want those benchmarks to be representative of real work. We're expert in Dask, we're experts in using Dask, but we're not really experts in knowing what end users need Dask for. So we could make something up in our ivory tower, but instead we want geoscientists to tell us about the workloads that they care about. So that's why I'm also asking everybody here in the audience who is doing geospatial work and who is very interested in one particular workload, even several working well, please tell us about it. We want you to help us help you. So let's come to the conclusion before we get to questions. What have we learned today? First of all, Dask and Xarray are a real power couple that allow us to scale our computations to the terabyte scale. And we're also working on Dask Xarray at the moment to unlock even larger scales, tens of terabytes, hundreds of terabytes. But we're not there yet. There are some fundamental problems in the way. And we're building up geospatial benchmarks that will help us guide future improvements and focus on the ones that really matter. So if you care about a specific workload, please propose a benchmark. Thanks. And with that, yeah, let's open for questions. I'll stop sharing real quick to jump to the questions. Can Xarray be used for multidimensional data frames? Xarray is mainly used for, or is just quote unquote, built for array computations. So like large scale grid data. It's not built for data frame computation. So if you want to use something like GeoParquet and combine that with GeoPandas, there is actually an integration that allows you to use GeoPandas in Dask. I don't know the exact name of that package, but just Google Dask and GeoPandas. That will point you to the right place. But those are like vector and multi-dimensional matrix workloads are two different pieces of the puzzle, I'd say. Do we have any other questions? Is P2P the default now? It is. If you upgrade to one of the recent versions, I think like since a couple of months, probably March, April, I'm not entirely sure. It's the default, but it's not always the default. What that means is that we have a heuristic in place that tries to decide when, like there are different trade-offs between the task-based implementation and P2P. P2P is great if you have these all-to-all communications. Task-based is great if you just need to rechunk things that are adjacent to one another. So for everything that's all-to-all, P2P is the default now, but we still try to make a smart decision about when to not use it. Does Xarray allow sparse arrays or dense? I am not entirely sure. I think it allows for both, but that's one of the points where I'm a Dask maintainer and not super deep in the weeds of the Xarray API. So I'll have to refer you to the documentation there. Did you separate computation of tasks into batches to prevent creation of large computation graphs in your demo? I did not. The computation graphs that we saw here were all the large computation graphs that Dask produces, for better or worse. Large computation graphs is actually one of the major problems that we need to focus on in the future, because they come up left and right when it comes to the scaling abilities of Dask.
All right. Thank you so much, Hendrik, and everyone else. Please join Discord so you can continue the conversation. You have a great day. Thanks again.
Thanks for hosting. Thanks, everybody, for watching.